Hello and welcome to Applications of Conservation Laws. So we've previously looked at the quarks and their properties. They have properties of charge, baryon number and strangeness. There is one more property that you need to be familiar with, and that is the lepton number. Now, quarks are not leptons, so they have a lepton number of 0. If you are dealing with a lepton, it's either going to have a lepton number of +1 or it's going to have a lepton number of -1. The leptons with a lepton number of +1 are the electron, the negative muon, the negative tau, and the neutrino. The leptons with a lepton number of -1 are the positron, positive muon, positive tau, and the anti-neutrino. What we're going to do now is we're going to have a look at a few particle interactions, and we're going to analyse whether or not these properties are conserved in the interaction. If they are, and everything is fine, then that is an interaction that can occur in nature. Remember that strangeness is conserved only in strong interactions. If it's not conserved, that can be an indicator of that it's a weak interaction. So strangeness doesn't have to be conserved all the time, but all of the others do. And if they're not, then that tells us that that interaction is not one that occurs in nature. So what we're going to do first of all is we're going to study a couple that we are familiar with, that we've studied before lots of times, and that we know occur in nature. And we're going to be having a look first at beta minus decay, and then beta plus decay, and then we'll have a look at a few others. Okay, so beta minus decay. We have a neutron decaying into a proton and an electron and an antineutrino. We're going to be studying what happens to the charge, the baryon number, the strangeness, and the lepton number. Okay, so the neutron is a baryon and it is made of an up, a down, and a down quark. The proton is an up, an up, and a down. So what's happening is that the neutron, one of those downs is decaying into an up, and as it does so, it releases these two particles. So let's look at the properties of all of the particles in this interaction and check whether these properties are conserved. Okay. So we know that a neutron has 0 charge. We can prove it by having a look at the quarks. 1 up and 2 downs, when you add those numbers together, plus 2/3, take away 1/3, take away the second third for the second down, and that gives you a charge of 0. The proton we know has a charge of 1, an up and up and a down. Add 2 of them, add 1 of them, and you get 1. The electron has a charge of -1, and the antineutrino has no charge at all. What we need is for the total on the left side of this arrow to equal the total on the right side of the arrow. So this needs to equal that, and it does. So we can say that this interaction is good. This is fine. The charge is conserved. Baryon number, the neutron has 3 quarks in it. It's a baryon. So's the proton. The electron and the antineutrino, they're not baryons, they're leptons. So that is also conserved. The baryon number is conserved. Strangeness, there are no strange particles in any of these. This is conserved. The lepton number, the neutron is not a lepton. Neither is the proton. The electron is, and it has a lepton number of +1. The antineutrino is a lepton, and it has a lepton number of -1. This part of the equation is equal to this side. So lepton number is conserved. All 4 properties are conserved. This is an interaction that does happen in nature regularly, and it's one that you've studied before. We're going to have a look at beta plus decay next. So beta plus decay is when you have a proton and it decays into a neutron. a positron and a neutrino. Let's look at these properties again. So we've got charge, baryon number, strangeness, and lepton number. Charge of a proton is 1, a neutron is 0, a positive electron has a charge of positive 1, and all neutrinos have no charge. This is equal to that. Charge is conserved. A proton is a baryon, so is a neutron. An anti-electron is not, and neither is a neutrino. This balances. Strangeness, we know that there are no strange particles in a proton or a neutron, and these are not made of quarks at all, so they can't have strange particles. So again, strangeness is conserved. Lepton number. This is not a lepton, this is not a lepton. This is a lepton, and it has a lepton number of -1. This is a lepton, and it has a lepton number of +1. Lepton number is conserved. So that's beta plus decay, and we've looked at beta minus. There's a couple more as well that we're going to have a look at, and if these come up in exam questions, you'll be given all the information that you haven't had to previously memorise. So for example, we might be studying something like a kaon, and normally you would think of kaons as, oh, they decay into pions. They don't always decay into pions, sometimes they decay into other things as well, and here is an example of a kaon decaying into something else. It can decay into a positive muon and a neutrino. Let's check to see if this is actually okay. Let's see if the properties balance. So we've got charge, baryon number, strangeness, and lepton number. So the positive kaon is composed of an up and an anti-strange, and then we've got 2 leptons over here. So let's analyse this. So we've got an up and an anti-strange. An up and an anti-strange, so that would be positive for an anti-particle, and that would give us a charge of +1. So that's got a charge of 1. The positive muon has a charge of 1, and a neutrino just doesn't have charge. And we can see that this balances. So this is looking good so far. Baryon number. This positive kaon has a quark and an anti-quark. It doesn't have 3 quarks. It's not a baryon. It's actually a meson because it's composed of a quark and an anti-quark. So what we can see is that the up has a baryon number of +1/3, and then the anti-strange would have a baryon number of -1/3, which cancels down to 0. It's a meson, it's not a baryon, so it has a baryon number of 0. This is a lepton, it's got nothing to do with quarks at all, and so is this particle. Baryon number is conserved. Strangeness. Here we have a strange particle. Remember that the strange quark has a strangeness of -1. The anti-strange has a strangeness of +1. So this has a strangeness of +1. That's a lepton, it's not made of quarks. Same with this one. So this is not conserved. So this tells us that it's either going to be a weak interaction if everything else is conserved, or it's not possible. This is not a decay that happens in nature. So let's wait and see before we make any conclusions. Let's look at the lepton number first before we come to those conclusions. So this is not a lepton, but these 2 are leptons. We've got a lepton number of -1, and we've got a lepton number of +1, which is conserved. So everything is conserved except for the strangeness. and that's okay if it's a weak interaction. So we conclude that this is an interaction that does occur in nature, and it occurs through the weak interaction. All right, let's do one more. Let's have a look at a neutral lambda particle. So this is one that you won't necessarily have ever come across before. We're going to study it. A negative pion, positron. Now the lambda 0, if you're given an interaction like this in an exam, you'll be told the composition of the particles. You should know that the negative pion consists of an anti-up and a down, and then you should know about the rest of these, which are leptons. Okay, so first of all we're going to do charge, then baryon number, then strangeness, then lepton number. So we've got an up, a down, and a strange. An up, down, and a strange. If you add all those numbers together, it cancels down to 0. We've got the pion, an anti-up and a down. So an anti-up is going to be negative, and the down, another negative, so that brings us to -1. This has got a charge of +1 and no charge at all. This balances. Baryon number, this is a baryon because it's made of 3 quarks. This is a meson because it's made of an anti-quark and a quark, so it's not a baryon. And these are both leptons, so they are not baryons either. And you'll notice that this does not 1 does not equal 0 + 0 + 0. Baryon number is not conserved, so it's looking like this is not a possible interaction. Let's continue with the analysis and see if there are any other inconsistencies. So we've got a strange quark over here, so it's got a strangeness of -1. No strange quarks anywhere else. So again, this is not conserved, which on its own would not usually be a problem, such as in this example here. But because the baryon number is not conserved, it's looking like, yeah, this is just not an interaction that occurs in nature. This is one that somebody's just made up. Finally, let's look at the lepton number. Not a lepton, not a lepton, is a lepton. And it's got a lepton number of -1. And finally, a lepton number of +1. So that is conserved. So it looks like the charge and the lepton number are okay, but the baryon number is not conserved, and that is a deal breaker. It might, if it had been conserved, it might have been an interaction that occurs through the weak interaction, but because the baryon number is not conserved, that just means that this is something somebody's made up. So that's how you analyse interactions to check for conservation of properties. Another important note to make is that energy and momentum are always conserved in interactions. That means that the energy that the particle had before is equal to the total energy of the products afterwards, and the same for the momentum.